group call. Super excited to have Peter Grant here as our main presenter. He'll be discussing some of the 120 volt phase 2 field study, which we've mentioned here on the call before. But we actually have some of our, sneak peek at our final results today, which is super exciting. We touched on some of the very preliminary results before. But now, yeah, we have a lot more meat of the report and field results to share with you today. So with that, Peter, can I have you read the antitrust compliance statement?
Sure, I can do that. So the Advanced Water Heating Initiative is a member-supported collaborative of professionals from across the U.S. This diverse membership includes numerous competitors, and care must be taken to scrupulously abide by federal and state antitrust laws. Members should remember that antitrust compliance is important at all times. At this and other AWHI meetings, participants should not discuss competitive pricing, profitability, allocating markets or customers, or promotion of a particular product or accessory.
Thank you so much. Sweet. So for our agenda today, we got our antitrust statement out of the way, and then we have some AWHI news and updates, and then I'll let Peter get into enabling utility heat pump water heater load shifting, which is again, super super excited to get all these charts and figures broken down about just how much load 120 volt heat pump water heaters can shift. So if there are any new participants in AWHI who have not been on this call before, you can take a second just to come on camera and say who you are, where you work for, and if you want, why you joined this working group. All right, sounds like no new faces today. So we will go to first piece of news is that AWHI released their 5-year report. So it's basically a synthesis of what AWHI has accomplished over the last 5 years. It's grown from a much smaller initiative to a nationwide effort now with far more members, far more support, and we've been able to accomplish quite a lot. And this is one of those working groups that's helping push the heat pump water heater market in a really positive direction. There's also the AWHI June newsletter, which I believe you should be getting if you're subscribed to this call. But otherwise, a bunch of news on what AWHI has been up to in the much more recent past. And then also very exciting is Heat Pump Water Heater Day on October 23rd. It'll be a whole day full of panels and presentations and interactive discussions on where heat pump water heaters are, what the future is, some of the history of heat pump water heaters. And so, yeah, definitely mark your calendars for that. It'll be a lot of exciting presentations, and I think we'll probably have some fun themes and heat pump costumes as always. And just lastly, here in terms of updates, the YouTube channel is up. I think we've talked about this before, but a lot easier way to access videos than having to comb through your email to find things. For me, for example, I was looking for a refrigerant video that I had missed, hadn't been able to attend the webinar, and super easy to find it on YouTube as opposed to, again, did I get that email or not? So very nicely formatted here. Catch anything you missed in some of the other working groups as well, and give you a chance to check out some of those and see if you want to join. So with that, I'm going to turn it over to Peter.
Well, that was pretty quick. All right. Thank you, Noah, for all that introduction. While I pull up my slides, did you say that there are heat pump costumes at the Heat Pump Water Heater Day?
Yeah, so well, Joe has his heat pump water heater costume. Joe Achunas, an NBI colleague. I think he's famous in this circle for dressing up like a heat pump water heater in a handmade costume for a heat pump water heater day. So definitely don't miss that.
All right. Well, that's good to know about. All right. Well, I'll just jump into the presentation from there. So I'm not as familiar with Teams as other platforms, so just want to do a quick check. Can everybody see some presentation slides?
And indeed.
All right. Thank you for that check. So yeah, the title of our talk today is Enabling Utility Heat Pump Water Heater Load Shifting Programs, and we're going to talk about some field results and tech transfer plans. This is talking about a project that Noah and I have been collaborating on for a while now, where we're doing load shifting with 120-volt heat pump water heaters spread throughout California. And we're working to develop tools that utility programs such as PG&E's Water Saver and Southern California Edison's Smart Shift Rewards programs can leverage. Um, so, little more background. LBNL is doing this work in the context of our CalFlex Hub and Store for Build projects. CalFlex Hub is a California Energy Commission funded project where we're really building a hub to develop, evaluate, demonstrate, and commercialize load shifting controls built around highly dynamic prices. So the thought here is that customers will someday actually see prices close to wholesale prices, and homes will have devices that automatically adjust their operation to minimize the operating cost in response to these prices. And in that way, we can provide people lower utility bills through load shifting while helping stabilize the grid, which becomes more and more important as we add more renewables. Simultaneously, we're also working in the Department of Energy funded Store for Build collaboration. And that project is all about advancing the state of the art and increasing market adoption of thermal energy storage in buildings. LBNL is pursuing 7 projects in Store for Build, one of which is focused on deploying large-scale load shifting with commercially available heat pump water heaters. So primarily leveraging CTA 2045 to send load shifting controls to heat pump water heaters out in the field. Another background slide that I've shared before is really talking about the philosophy behind the controls that LBNL has been developing. And historically, we've seen a lot of load shifting controls that were not customized. It was a single engineering solution applied, or yeah, a solution developed using engineering judgment applied to all of the heat pump water heaters in a fleet. And I think we all know that different people behave differently, right? As the plots in the upper right show, some people consume a lot of hot water in the morning, others consume a lot of hot water in the evening. Sometimes people go on vacation and consume almost no hot water at all. And these different behaviors lead to different electricity consumption profiles, right? Sometimes people consume a lot of electricity in the morning, sometimes a lot of electricity in the evening, sometimes almost none. And these 3 different cases would get the lowest operating cost of the heat pump water heater with 3 very different load shifting signal schedules. And so our entire philosophy is based around figuring out how to identify the different baseline behaviors in homes and create load shifting schedules that yield nearly optimal results for all these homes, given the challenging realities that we don't have flow meters and that people don't do the exact same thing every single day. So there's a lot of uncertainty and variability here. I kind of got ahead of myself, but so this slide talks a little bit more about how we're approaching it. And basically, we created ways of grouping heat pump water heaters based on their baseline electricity consumption. So we can identify homes that have, fairly similar behavior. Then we use those groups to generate cost minimizing CTA 2045 signal schedules, an example of which you can see up on the top of the plot. And then we send those signals to the heat pump water heaters at different times of day. And we can get some pretty darn good results, as you can see at the bottom. So this plot, especially the bottom plot, shows the times when the electricity price is above average, highlighted in the red background. Then what we anticipate happening with the control logic of one manufacturer's products in the blue dashed line. And then what we anticipate happening with LBNL's control signals in the green solid line. I should point out this was simulated data with a fleet of 148 heat pump water heaters. And we found that we could optimize the use of existing storage. That's one of our selling points in Store for Build, where they constantly talk about how we get people to install phase change material. Well, why do that when we have existing storage that's already paid for that we can start with? We found that in this case, we could shift 77% of the load away from high price times of day to low price times of day. And conveniently, we shifted it to create a big peak right when there's a lot of solar being produced by PV panels. So we can help solve that problem that's common in California. And we reduced the operating cost of the heat pump water heaters by 29%. So homes that participate in this would see a reduction on their utility bills. So this is all great. And now we're talking about how we're transitioning all of this from the simulation environment to the field. And so we've been working with NBI. This is one of Noah's slides, but I'll present it on his behalf today. And NBI previously had performed a phase 1 field study on 120 volt heat pump water heaters throughout California. They installed 32 of them, monitored their performance for over 12 months, and evaluated the performance and found that people were really quite satisfied with them. They were able to deliver hot water, just as much as people needed, which that was the main concern that people were looking out for. So yeah, pretty satisfied with their performance. And NBI has published a report, so you can find that report online and read more if you want to know more about that project. So with all of that background, we went into a project doing field verification of these controls, having modified them to 120 volt heat pump water heaters. And there were a few important research questions that we wanted to address in this study. One is just about the capabilities of the water heaters, right? We heard that they don't necessarily respond to advanced load up. We're also aware that sometimes the 120 volt products have a higher set temperature for the tank than what the user specifies. And if that's high enough, even if the product's, from a communications point of view, capability of responding to advanced load up, then the heat pump won't actually be able to raise the temperature anyway because it's already too high. So we wanted to evaluate just how important advanced load up is for the load shifting controls. Then we wanted to evaluate in the field how well load shifting controls perform with what I'm calling quasi wholesale prices. So those are the prices that we're using in the Cal Flex Hub research project. From there, we wanted to bring this, provide some grounding based on current electricity prices. So we evaluated how well the controls work with current time of use rates from actual utilities. And then we did a little bit of work evaluating what characteristics of these rate prices really support load shifting and drive good results, and what characteristics maybe aren't the best. And we're also starting to look into how we can transfer this research to utility programs. So that's the efforts underway right now. So the first topic there was about the advanced load up and how important it is. And we did some simulations. We also did some field testing, but this slide talks about the simulations, evaluating how much impact it has. And so you can see in the top of these subplots a price curve. That's the CalFlex Hub summer electricity price. And then down on the bottom, you can see similar to the plot we had before, the red shaded period is the time when the price is above average. So we're trying to avoid consuming electricity then. The middle plot shows the electric power, with blue showing what happens with no load shifting controls and green showing what happens with load shifting controls. And then the bottom plot shows the operating cost of the heat pump water heaters, given that price curve and that demand curve. So as we dive into these plots, we can see a couple things. One is that without access to the advanced load up, we really couldn't increase the electricity consumption to increase the energy stored in the tank when the prices were low very thoroughly. Even without the load up command, these water heaters were pretty darn close to fully charged at that time of day. So when we sent the load up command, not many of them actually responded. And so they increased storage a little bit, but not all that much. And it's a little small, so I called it out, but you can see that the maximum value here for the 148 heat pump water heaters is about 40 kilowatts. Now, if we jump over to the situation with advanced load up, you can see that suddenly the electricity consumption during that low price time of day doubles, and the maximum is all the way up to 80 kilowatts. And this is because suddenly we have all 148 heat pump water heaters consuming electricity and dramatically increasing the amount of energy that's stored in the tank. Now, the next part shouldn't come as much of a surprise there, but because we were, well, without advanced load up during the high price period, we were able to use the shed command, and that did significantly reduce the electricity consumption during the peak period. But that does also create a risk of sending cold water to the occupants. And it's, the heat pump is going to turn on when there's a risk of that. So we could only reduce the demand during the peak period by so much. Whereas in the case with the advanced load up command, there was significantly more energy stored in the tank. We were able to reduce the risk of occupants receiving cold water, and we were able to dramatically reduce the amount of electricity consumed during the high price period. So as I'm sure is no surprise, when you look at the operating cost of the water heaters, you can see there's a much larger reduction in operating cost during the peak period with advanced load up. And also, since the low price during the middle of the day was actually down all the way to 1 cent per kilowatt hour, the increase in operating cost from running advanced load up during that midday period is completely negligible. So without advanced load up, we were able to reduce the operating cost by 32% and the peak kilowatt hours by 29%. With advanced load up, we were able to increase those to 53% advanced or operating cost reduction and 60% peak kilowatt hour reduction. So we really just want to highlight this is important. These capabilities really help drive good results for owners of heat pump water heaters if they're used intelligently. So we also moved on to doing field studies, looking at how these 120 volt heat pump water heaters in the field respond to the load shifting controls. I forgot one important comment on the previous slide. We did some field testing, both with and without advanced load up, and we found that the products that were installed in the field were not responding to the advanced load up. So all the rest of these slides assume that advanced load up is not an option and are limited to using the load up and shed commands. We did start conversations with the OEM of both the water heaters and the modules, the CTA 2045 modules. So hopefully they're getting to the bottom of that, and this will be resolved, and advanced load up will be an option in the future. So now moving back into the field study results. So this slide is going to talk about the results of load shifting with the 120 volt heat pump water heaters with the Cal Flex Hub price curve that represents potential prices in the summer. And you can see there's a really big differential in the price, right? Overnight, it's down around 3 cents per kilowatt hour. At 9 a.m., it's about 1 cent per kilowatt hour. And then in the evening peak, it's 78 cents per kilowatt hour. So there's a huge economic incentive to shift load. And we developed load shifting control signal schedules that were customized to this price curve. And we found that we were able to reduce the load during the high price period by about 52%. And all of that load was shifted towards times of day when the electricity prices were lower. Pretty clearly shown on this plot that a lot of it was shifted until after the price is reduced. So the heat pumps were running overnight to recharge the tanks after shedding through the high price period. But you can also see in the midday period that there was some increase in load, and so there was some use of the load up command to increase energy stored in the tank. Then because we reduced the load so much during the high price period, we also reduced the operating cost significantly, and we showed 46% reduction in operating costs. One other thing that's interesting and worth noting here, I'll go back a little bit to get these circles out of the way. But you can see right here that there are two different jumps in the electricity consumption. And this is a case of snapback where the water heaters come out of the shed mode and the water in the tank is cold enough to operate the heat pump, once they're no longer in shed mode. So the heat pumps start kicking on. And, it's a real challenge for the utilities when all of these heat pumps activate at exactly the same time. But one cool impact of the Cal Flex Hub prices is since it's stepped and changes every single hour, some heat pumps are kicked on right at one time, and some others kicked on at another time. So we end up with this two-stage snapback, which should be easier for the utilities to manage than if they all happened right at one single time. So that's an example of the CalFlex research. From there, we moved on to studying the impacts with current utility time of use rates. And we chose 3 different time of use rate structures, really trying to represent not the utilities prices directly, but different characteristics of different types of price curves, right? So we're not doing a PG&E versus Southern California Edison comparison. We're doing an EV price curve versus time of use price curve comparison. So we chose 3 of them. One of them is an EV rate. We chose it partly because these are rapidly becoming more and more common as people are adopting electric vehicles, and also because it has very high peak prices to really incentivize shifting load away from the peak. And we wanted to study how well the controls would work in that environment. We also chose one primarily because it has a reduced midday price. So we were looking here for not only incentive to shift load away from the peak period, but also incentive to shift load towards that midday solar production peak. And we chose a third one where the price gradually increases throughout the day, because this is pretty common. This is how a lot of the time of use rate schedules in California work these days. And we wanted to capture something fairly typical. So if we look at the EV rate, we can see that we did dramatically reduce the electricity consumption during that high price period, a 54% reduction. And this is because, again, the prices were very, very high. So the controls used the shed command to coast through that peak period as much as possible without consuming electricity. But we can also see that the typical load during that high price period in these heat pump water heaters was not very high, right? It was averaging about 200 watts, which in a fleet of 4 heat pump water heaters, 200 watts means on average approximately 1/2 of a heat pump is activated, which basically means, one heat pump is activated on 1 out of 2 days. You can't actually turn on a half of a heat pump. So the load was pretty low, right? And while we did reduce it by 54.2%, let me jump forward. While we did reduce the peak load by 54% and shift that load to other times of day, we only got about an 8.5% cost reduction because that peak load was just so small to begin with. We did also notice that we had an error in the controls. It was designed for the more smoothly transitioning CalFlex hub prices, and we noticed that that led to a design decision, which actually caused the heat pumps to come out of shed mode half an hour earlier than they should have. And so we have corrected that now. We also did some post-processing and found that without that error, we would have reduced the bills by about 9.8% instead of 8.5. So a little bit better. We also saw that there was snapback every single time, right? With all of the water heaters going into shed mode to avoid consuming electricity during the high price period. As soon as they all came out of shed mode, every single heat pump turned on every single day. And so that's a challenge that the utilities would have to face, assuming that price curves have this shape. We also did one focused on your one price curve where the price was reduced during the middle of the day, right? And so we wanted to evaluate how that would impact the load shifting controls. And we do see that the low price prior to the high price caused an increase in consumption during the midday period. Typically, the fleet averaged about 50 watts right before the high price period, which basically is a way of saying that people took their morning showers, the heat pumps activated to recharge the tank. By the time you got to later in the afternoon, the tanks were charged, the heat pumps were not operating. On roughly 1 out of 10 heat pump days, a heat pump would turn on. So it was pretty rare that they were heating at that time. But when we started sending the load up command, you can see that it increased to about 500 watts. So we're increasing the typical demand at that time of day by about 10x. And because of that, we're able to pre-charge the tank at these low electricity prices. So that was a good result. One quirk, though, is that these heat pump water heaters were typically fairly low users, and the controls actually found that the best strategy was to shed for the last hour of the high price period, not for the full high price period. And so in the test case, you can see that the load did start picking up as people consumed hot water and the heat pumps kicked on, and then rapidly shut it down 1 hour before the high price period ended. That's because of this issue in the controls. So right now we're reevaluating whether or not that's the right choice, right? Maybe the algorithm says only shed during the last hour, but maybe we should change that to be shed during the whole, 3 hour high price period. Um, but also maybe that increases the risk of cold water events too much, and we don't want to do that. So, we still need to do some further analysis figuring out the right decision here. Um, but
I
one
think
other thing
Tristan
you
had a quick question.
Oh yeah, go for it, Tristan.
So as a module maker, right, even though CTA 2045 has no official way to resolve snapback, I'm sure every module maker, we certainly talk about it. We haven't had to do it yet because we haven't had scale, but all the module makers could easily group and feather the snapback. We've talked about groups of 10, for example. So just kind of pointing out that just because it's not in the CTA 2045 spec doesn't mean that module makers can do it at their sort of application level.
Yeah, that's absolutely something that could be done, and we would definitely support doing that. I would add to that we should consider feathering on the load up as well. We've seen simulation results, with our fleet of 148, which is much higher than 3 or 4. And you can see that if you send the load up signal to the whole fleet, suddenly 148 heat pumps kick on, right? And that's a massive spike in load, which would be a challenge for the utilities. Um, so we should consider feathering both the releasing the shed and sending the load up signals.
Right, and just as a quick follow-up, we're dealing with soon 145 electric resistance water heaters. And what's interesting is it would be interesting to compare their ability to feather versus not, right? There's only 5 more years of electric resistance water heaters, but they can load up in 5 minutes a lot faster than a heat pump. So you can do groups of 10 in an hour in 50 minutes at 5 minutes each and get them all fully heated. That may not be as possible with a heat pump. The feather might have to be 2 hours out, and then that's more problematic.
Yeah. And since those electric resistance elements consume about 8 or 9 times as much electricity, boy, feathering them makes a lot of sense, I think, because that could create a much larger spike. Yeah. Okay, so another thing to point out on this reduced price or midday rate structure is that we did not see any snapback after the end of the peak period. And that's probably because of a combination of things. One is because of how well the tanks were pre-charged going into the high price period. Also, probably because we didn't shed as much, which, meant the heat pumps were able to keep the tanks charged. And also probably because the high price period was fairly short, so not all of the homes consumed enough hot water during that peak period to need the heat pumps to turn on afterwards anyway. Um, and so looking at the overall costs or impacts of this price schedule, we did manage to reduce the peak kilowatt hours by 29% and the operating electricity costs by 19%. So there are benefits for both the utility and the participants there. So then the last one was one with a gradually increasing price structure. And we would ideally want to see load up both right here, at the end of the lowest price and right here at the end of the, slightly increased price to keep the tank really charged up going into that highest price period. And what we saw was that it did load up at the end of the lowest price. So we had those tanks fairly charged going into the elevated prices. Then we also tried to load up again right before the prices dramatically increased, but the tanks were too charged, right? They were already charged up from the previous load up, and so we couldn't really add much energy to the tank at that time. Fortunately, as you can see in the plot, these users were fairly low electricity consumers during the highest price period, so that's probably part of why the controls were set up this way. We just didn't necessarily need it to work out well, we just didn't necessarily need more modifications to avoid consuming during that high price period. Um, then you can also see significant snapback as we came out of the high price period, right? These water heaters were put into shed, and when they came out of shed, several of them were cold enough that they needed to turn on the heat pump. So that was that's not an ideal result that came out of this price curve. So if we do a high level comparison, I talked about these four bottom ones here today. We talked about the CalFlexHub winter highly dynamic price at a previous one, so I skipped it today. But we can see that there were some very different results depending on these different price curves. The CalFlexHub price curves and the EV rate both had the highest prices during the evening peak period. And I don't just mean that in terms of like highest price for that price curve, but I also mean in comparison to the other electricity price curves that we studied, which really provided a lot of incentive to shift load away from the peak period. So you can see those three had the largest peak kilowatt hour reductions. From there, the CalFlexHub prices had the largest, what we call dynamic range. Dynamic range referring to the difference between the lowest price and the highest price. And because they had those really high dynamic ranges, there was a lot of economic incentive to shift load, which resulted in the largest reductions in operating costs. So from there, right, the price curve with the reduced midday prices did also see a dramatic reduction in the peak kilowatt hours consumed of about 30% and an operating cost reduction of about 19%. And it also provided incentive to shift load right to that midday period. So one thing we noticed a lot in the CalFlexHub prices is that since the curve or since the price kind of gradually increased, there was a lot of time with high prices. And so these load up command didn't actually help very much. And it ended up relying on the shed command to shift load to the overnight period instead of to the midday solar period. Now that changes dramatically with the advanced load up, but given the limitations we had, this was the result we found for the 120 volt heat pump water heaters. Then the EV rate we found, it did dramatically reduce the peak kilowatt hours. But given that price structure and the typical behavior of those occupants, we only saw about an 8.5% reduction in operating cost. So that's something that could perhaps be improved in the future. So from there, right, now that we've done these studies and we've developed tools to be able to do this, we're starting to work on creating tools that utility programs can leverage to use these approaches directly in their programs. And this slide so far is content that I've shared here before. And this talks about how we create groups of heat pump water heaters. We've simulated 148 water heaters using a model that closely matches one manufacturer's product. So we're confident it's pretty accurate. And then we group these heat pump water heaters based on similar electricity consumption by calculating the root mean squared error. And root mean squared error is a metric that looks for differences at every single time step, right? So if one heat pump turns on literally 15 seconds later than the other, the metric notices that difference and pushes, a larger root mean squared error. So these products are less likely to end up in the same group. And you can see this leads to some very tightly clustered groups, both in terms of timing for electricity consumption and in terms of identifying which water heaters do use electric resistance elements. I should point out just one quick caveat. The 120 volt products we were studying do not have resistance elements, so that plot on the bottom is clearly for 240 volt heat pump water heaters, but really wanted to highlight that it can notice those. Now this creates a lot of groups and it's probably unrealistically closely clustered, and it's not even truly the information the utility programs need, right? They need to know what time of day the water heaters consume electricity relative to the price curves that their occupants or their participants are paying. So we're currently working on updating that algorithm. And instead of calculating root mean squared error based on every 15-second time step, we're creating a tool that creates periods throughout the day based on the price curve. So you can see an example of that in the bottom right, where we have 4 different periods we're studying. 3 of those periods are defined by the electricity price at that time of day. And then the 4th period is showing what we're calling the morning shower rush. So this is when people are going to consume most of their electricity through the water heater responding to them taking showers in the morning. And if they happen to have a 240 volt water heater, this is when they're most likely to activate the electric resistance element. And so we're looking for differences in that control and that behavior, as well as just changes in the timing. And then we're going to create groups based on how the water heaters respond in those different times of day. And so that will create simulated groups of water heaters. And from there, the utilities will need to know which group a new water heater that they have in the field applies to, so that they can know which customized group of CTA 2045 signal schedules that heat pump water heater should receive. And so the question is, how do they add this new heat pump water heater to a group? So we're suggesting that we can stop thinking of them as heat pump water heaters and start thinking of them as baseline electricity curves. And the CTA 2045 module does enable you to get electricity consumption, so you can create those curves. And once we have that baseline electric curve, we can put it into each of these different groups, right? Assume it's in the group. And then we can calculate the root mean squared error of that curve compared to the curves in each group. And we can identify the curve with the group, which returns the lowest root mean squared error, which is a way of saying that the heat pump water heater at this site most closely matches the heat pump water heaters in this particular group. And then the utility program can start sending the CTA 2045 signal schedules for that group out to that heat pump water heater. So we are in the process of developing these tools, and PG&E's Water Saver program is hoping to start experimenting with using them and just, be an alpha tester and see how well they work and how well we need to update them in Q3 of this year. So pretty soon. And that's what I had for you today. So thank you, and happy to open it up for discussion.
Thank you so much, Peter. That was awesome. Yeah, let's definitely open it up for questions. Anybody is welcome. Just raise your hand or just pop off mute and ask a question. Looks like we do have a hand here. Tristan?
Just a quickie, Peter. That last sort of analysis of root mean squared to determine how to put it in a group. Do you know how many weeks you would want to be observing a water heater before you did that? Or is it days or weeks? Or do you have a sense of that yet, or more later?
I think that's an important research question, to which I would say more later. We do know that Water Saver collects 4 weeks of baseline data prior to including a heat pump water heater in their load shifting program. So we're going to try 4 weeks, and we're going to see how well it works and go from there.
Bruce?
Yeah, a real minor point here. It may seem like inside baseball, but I would discourage any of us from using the term wholesale price in relation to retail price. We've had 140 years of having no relationship between wholesale and retail prices. And while we might be better off if we calculated retail prices from wholesale prices, that is absolutely not the right answer. And we need to disabuse people of that idea. So certainly there might be some relation between the two, but we want to calculate retail prices based on what produces the best overall result, which will not be a direct calculation from the wholesale price. I think the key is that we want them to be similarly dynamic. In fact, ideally even more dynamic than wholesale prices.
All right, we'll have to talk offline about my nomenclature, Bruce. I'm trying to find a better term than research price, and apparently haven't hit it yet.
Well, it's only the mention of wholesale, but in any case, that has nothing to do with the content of all the optimization, which is awesome. So thank you.
Cool. Any other questions for Peter?
Well, that was easy.
I had a quick question about you had mentioned ramping is something that's valuable and important. Did you look at that at all when you were doing any of your advanced load up commanding?
When you say ramping, I assume you mean like feathering the load up so that heat pump water heaters come on sequentially instead of all at the same time?
Yeah, there's start and stop randomization built into the advanced load up protocol.
Okay. So I don't know if there is anything built into the protocol. I would have to double check that. I know for our simulated work stuff we were doing, gosh, I guess this was almost 2 years ago now.
Cool.
I would have to dig around a little bit to find slides to share, but we did find that if we just sent the signals out, without any sort of feathering, we would see sudden spikes of like 60 kilowatts. On a fleet of 148 water heaters, that's a pretty big spike. Imagine if it was 7 million water heaters.
Mm-hmm.
And then those heat pumps would often turn off like 30 seconds later, which is a way of saying, the water in the tank was just barely shy of the set point, but it wasn't actually at the set point. So all the water heaters kicked on for a tiny bit of time to bring it up, and then it just shut
Mm-hmm.
off. And if this happens every hour, that's a nightmare for the utility. So we created an algorithm that looks at the state of charge of the storage tank. And that's something that, you can't get the state of charge via CTA 2045, but you can get take energy, which is, basically a measure of how far below fully charged the tank is. So we could, slightly modify our algorithm to leverage that capability. And then we set it up such that there was a threshold, and the signal only gets sent out to water heaters that are below that threshold of state of charge. And then every couple minutes, the threshold increases by a few points until it's up to a state of charge of 100, and everything's gotten the signal. And so if we go back all the way to the beginning, got a lot of clicking to do to get there. Here we go. So this curve right here, that's how we got this ramp instead of just a sudden spiking behavior like that. Does that help?
I think so. So this is all simulated data.
So the slide that I had right here, this is simulated. This is also simulated. Everything from here forward is field monitored.
Gotcha. Thank you.
Yeah, great question. And we did another question in the chat. What were your assumptions for the ambient temp and rate of heat transfer efficiency for this study? I can answer the first part. We didn't have ambient air temp assumptions because we did have detailed monitor equipment. So we knew what the inlet and outlet temperatures were at all times, when we also knew what the ambient air temperature was, thanks to using thermistors. But I'll let Peter take the heat transfer efficiency as well.
Mm-hmm. Yeah, so when developing the control strategies, we were using typical California garage assumptions for ambient temperatures. And so for the heat transfer efficiency, is that referring to the COP of the heat pump?
I would
Yeah,
believe so. Oh, sorry.
yeah, go ahead. Sure.
Okay. So we do have a model that's calibrated to closely match one manufacturer's products, and that does include the COP of the heat pump. We've gotten pretty good results, both in terms of the heat transferred to the water and the electricity consumed. And so basically we were assuming that we were using that manufacturer's heat pump in the efficiency.
Yeah, because it was just a single manufacturer in the study, so at least that helped us, not have to account for more variables in terms of performance there. Ideally, they were performing at a similar rate. There were different tank sizes, so I guess that can have its impact between 50 and 80 gallons, but otherwise, ideally, a similar COP. Then I also had a question, Peter. So the CalFlex Hub prices are highly dynamic, and as you presented today, that's very helpful in maximizing savings, maximizing load shift away from peak periods. Is there a way to try and promote these prices? Do you think the market will naturally become more dynamic in terms of utility prices? I guess this could be a question for Bruce as well.
Yeah, I was going to say that my answer to that question is that I'm very glad Bruce Nordman is on this call. Bruce, would
Yeah.
you like to jump in?
Sure. Well, California is planning to introduce hourly prices starting in 2027.
Mhm.
How good those prices are in terms of how much opportunity they give people to save money is unclear. Also unclear is how simple or complicated this whole system is made. I favor simple. I think
Yep.
the best things in life are simple and universal. A month ago, I was in Denmark, where they've had hourly prices for several years already, and everything works just fine. And people are starting to introduce automation. They introduces the prices first, and then started thinking about the automation. We're kind of doing it the other way around. We're thinking about the automation without any prices. But without any prices, we really limit the possibility of businesses to actually do anything because they can't actually offer customers the ability to save any money. So the sooner we have the actual prices, the better, so that we can actually move into the future instead of staying stuck in the past century.
Absolutely. That's a good answer. Thank you, Bruce. Awesome. And I saw a question in the chat. I'm just gonna make this, everybody aware of this. When will the info be published on YouTube? And so that's generally speaking, early the week after of the presentation. So that'll probably be Tuesday or Wednesday of next week, and that's when I'll follow up with both the slides and the YouTube link as well. And just one more general admin note. The next meeting will be July 19th. At the same time, we stopped having the recurring meeting schedule just because things were bouncing around a bit, but I will try and get those meetings up on everyone's calendars so you can have more time in advance to plan and know when attendance will be happening. But anyway, any other questions or is that it for today? Awesome. Well, thank you so much, Peter, for presenting. That was excellent. And great to see you walk through all of this.
Yeah, sounds good. Happy to do so, and thanks very much for the opportunity to continue sharing CalFlex Hub and Store for Build research with the broader community.
Yeah, absolutely. And I think, as Peter was mentioning, these findings are definitely transferable to larger programs. And I think that'll be an awesome next step in the future is, how do we go from that 3, 4 water heater fleet to hundreds or thousands of water heaters? So that's definitely where some of our research will be focused next. But yeah, well, thanks everyone for attending, and we'll see you at 9 a.m. on July 19th. Have a great weekend.